As a next step, we will formalize the intuitive ideas presented in the introductory video and developed in the toy example covering the good-bad driver setting. We consider a portfolio with N contracts or policies, each observed during TI periods. I refers to the contract or the policyholder considered. Note that the data may be imbalanced, that is, the period of observation may be different across different contracts. We will be working with claim frequency data, that is, during each period T, the number of claims reported is registered. Let NIT be this number of claims reported for policyholder I in year T. Year T hereby runs from time T-1 to T. For example, the first year runs from T equals 0 to T equals 1. Time 0 here represents the policy issuance. Putting these things together, we have the following nested structure. Each policyholder or contract I generates a sequence NI with the claim numbers registered in period 1 up to TI. We assume independence between the different contracts, whereas positive dependence is expected within a vector NI. That is, the number of claims reported by policyholder I during a certain period is expected to reveal positive dependence with the number of claims reported by the same policyholder during a different time period. We now combine the experience on contract I as registered over the different time periods with the random risk variable theta I, which expresses the riskness of contract I. These combined sequences are assumed to be independent for different policyholders I. The risk parameter or risk random variable theta I requires some reflection. It is a random variable expressing the risk proneness of policyholder or contract I. It kind of captures the characteristics or features on policyholder I that cannot be expressed via observable risk characteristics. Therefore, it is a random effect summarizing these unknown characteristics or this unexplained heterogeneity between contracts. From a math point of view, given the random variable theta I takes value theta, we assume the random variables ni1, ni2, etc. to be independent. We are now ready to define the so-called Poisson credibility model. Each policy or contract I in this model is represented by a sequence theta I and then a vector ni. Here, theta I is a positive random variable with unit mean, which represents the riskness or heterogeneity that cannot be captured with the observable risk factors used in the a priori rating model. And two assumptions are postulated in this Poisson credibility model. Assumption 1 states that given an observed value theta for the random risk variable theta I, the random variables NIT are independent and follow a Poisson distribution with parameter lambda IT times theta. At the level of the portfolio, the sequences theta I and I are assumed to be independent. Now, the fact that theta I has positive support is straightforward to understand. Given theta as a realization of this random variable, you see that the mean of the Poisson distribution is lambda IT multiplied with theta. And that construction only works if the mean is positive, thus the theta value should be positive. Now the unit mean restriction relates to our comment on financial balance. So overall, the expected number of claims will not change through the a posteriori corrections that are imposed. Applying the Tower rule then shows that the expected value of NIT is lambda IT with under the assumption that your random risk variable theta I has unit means. So that's where this assumption is coming from. Now this setup is a classic actuarial construction for experience rating. Dependence between annual claim numbers reported is a consequence of the heterogeneity of the portfolio, that is, of the fact that the random variable theta I is shared by the variables NIT for fixed I, but where t runs over time. Recall that the theta I random variables capture unexplained heterogeneity between different contracts or policyholders. This heterogeneity, frailty, or risk proneness will be revealed by following the contract over time, that is, by the claims and premium histories as observed over time. This observed experience will modify the distribution of theta I in a Bayesian way, that is, by using the posterior distribution of theta I given the observed number of claims in the first period, the second period, and so on. So by using this posterior distribution of theta I, we will be able to modify the premium of insured I or policyholder I via an a posteriori correction. And this will be the topic of the next sheets. So we will now work through some basic calculations within our Poisson credibility model. Let NI bullet be the total observed number of claims on policyholder I, and lambda I bullet be the total expected number of claims for policyholder I during the TI observation periods. As mentioned earlier on, the idea is to gain insight in the distribution of theta I, the random risk variable, in a Bayesian way. That is, by using the posterior distribution of theta I, given NI1, NI2, and so on. In our Poisson credibility model, this distribution of theta I will only depend on the total number of claims reported on contract I. That is, the conditional probability that theta I is less than or equal to t, given the claim history, reduces to the conditional probability that theta I is less than or equal to t, given the total number of claims registered in the past on policyholder I. Now let us check mathematically the claim that was made on this previous lecture sheet. That is, the fact that in our Poisson credibility model, the conditional or posterior distribution of theta I, given the claims reported by policyholder I, only depends on the total number of claims reported on this contract I. To verify this statement, we start from the conditional PDF of the random risk variable theta I. In this conditional PDF, we condition on the number of claims reported by policyholder I, and we use the notation NIT to denote the random variable that expresses the number of claims reported by policyholder I in time period t. And we use the notation KIT to denote the actually observed number of claims. The sum of all the observed claims reported by policyholder I is then denoted with KI bullet, where the sum runs over all observed time periods t, going from 1 to ti. Now the first equation in this expression rewrites the conditional probability density function as the joint distribution of theta and the random variables ni1 up to niti, divided by the joint distribution of the count random variables. That's just a matter of applying the definition of a conditional probability density function. Now the extra notes available in your lecture material will give you more details on the derivation of the final expression here printed at the bottom of the sheet. So what do we learn here? Note that the conditional probability density function of theta only uses the lambda I bullet and the ki bullet in its final expression. As such, the property from the previous lecture sheet holds true. Our Poisson credibility model. In our Poisson credibility model, the conditional or the posterior distribution of theta I given the claims reported by policyholder I only depends on the total number of claims reported by policyholder I. Now let us give some intuition or interpretation to this property, and therefore we rephrase this insight as follows. The Poisson credibility model, as determined by assumption 1 and 2, disregards the age of claims. Only the total number of claims reported in the past matters. In this Poisson experience rating scheme, the penalty induced by an old claim is identical to the one induced by a more recent claim. And of course, a natural reflection is then how realistic would this be in a commercial setting. The Poisson model as proposed so far is an excellent model to start from and to show the Bayesian thinking that is involved in credibility models. Once you understand this setting, you're ready to explore more complex credibility models. For instance, a dynamic setting where the timing of claims reported in the past would be taken into account. Now, having the posterior distribution of theta I given the reported claims at our disposal, we will now continue with the conditional distribution of ni ti plus 1. This is the random variable that represents the number of claims reported in the next period of time, ti plus 1, by policyholder I. The distribution of this random variable, representing the number of claims in the future given the past observations, is called the predictive distribution. Note the similarity with the terminology used by Bayesian statisticians. We derive an expression for this predictive distribution. This derivation is fully documented in the extra notes available in your course material, and at this point you should verify this derivation. Having our expression for the predictive distribution of ni ti plus 1 available, it is insightful to rewrite this predictive distribution using our expression for the conditional distribution of the risk random variable theta I given the past claim history. That is the expression derived on sheet 24 earlier on. Using this expression allows us to rewrite the predictive distribution into the expression at the bottom of the sheet, where we recognize a Poisson probability function with a parameter lambda I ti plus 1 times theta, where the theta is a random draw from the posterior distribution of theta given the past claim history. Recall that lambda I ti plus 1 is the a priori expected number of claims for policyholder I in time period ti plus 1. It is the risk assessment made for this policyholder in the next time period, when only a priori characteristics would be taken into account. Now, recall from our course on risk modeling in insurance that we discussed there the use of Poisson mixtures. And what we learn here on the previous sheet is that the predictive distribution of the number of claims in the next time period, given the claims reported in past periods, is a Poisson mixture, where the mixing distribution is now the posterior distribution of theta I. This ends our introduction of the Poisson credibility model. You're now ready to derive estimators for the posterior premium of policyholder I in the next time period, and that will be covered in the next videos.